So today we are going to finish off with LZW. We'll take another example and we'll finish off with two other source coding techniques, and that will be the end of our discussion on source coding. Oh, wow. What has happened? Is it visible at all? Okay, so we'll take this example. Again, the screen. There's an issue with this. Okay. So, suppose the initial dictionary for this LZW is given as this. So, this is my index. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the 10 initial index is given, and for respectively I have been given as the entries as, so the entries are given over here as S, P, T, B, R, E, A, space, O, and N. So there are 10 entries in the initial dictionary set, and the message that we need to encode, this is only the encoding we are doing, the decoding will be the same as I told you. So the message that we need to encode is readers space readers bed spreaders spread reads spreads, this is on bed. So this is the message you need to encode using LZW technique. So encode this following message using LZW method, which we did last day, and tell me the tabular entry, what are the values you are getting. Okay. We'll quickly finish off this and then we'll move on with the next one. Encode the following sequence or the following sequence of symbols, whatever you call it, using the LZW technique. Just important to observe that in this case also we will follow the same way like we did in the previous example. So you have the current symbol, Then you have the next symbol. So next symbol, then you have the encoded output. Okay. And then you have entry, the new entry, that is the concatenated entry, and the new index for that. So you have to follow the same process in order to fill up the whole table. As I told you that you can do any such problems if you know the process, any one process, because it will be repeating for the other problems as well. You just have to understand one and the others will be quite okay. So again, it's just to repeat in few lines. Like first we'll start with the word B. So since B is there, we'll write it the current symbol as B. And B happens to be in the place of 4. So the entry initial dictionary is 4. So your encoded output will be 4. Your next symbol is E, which will be written over here. But also you have to write it over here, because BE being the new entry or the concatenated entry, you should have it after 11. That's what I told last day. We had 5 symbols here in the last example. But here we had 10 symbols which is in the first entry. So your next entry, the new entry, will only be at the 11th location. Okay. So your 11th location will be nothing but the process of BE. So that's how it is. In the same manner, E, if it is there, E is already there in the existing dictionary. So E happens to be 6. So your encoded output should be 6. But the next symbol you have to check is D. And D comes over here. But D also comes over here. You can, for your reference, I have seen in many of the PDFs which I have referred to, they are giving something like this as for the illustration as well as for your own follow-up leading towards the encoder output. You may use this arrow like this in order to make sure that you are only able to understand that how the process has developed. Okay, so that also you can do. So ED being a new entry, ED will come over here and you will have the 12th entry as this. So like that you just go through the whole sentence. I will give you at max 5 minutes, 5 to 7 minutes. Finish it off and tell me the answer. Because it's the same process we did already. I'm not going to do the whole thing once again. It's just that I wanted to give you an example of other nature or values or symbols which are more than 5. So, and also one important note that I told you, that whenever you are making this entry, make sure that you have the entries based on the first possible non-existing element when you are doing the concatenation. For example, at some point of time you might receive space SP, something like this, I guess. Somewhere you will get it. Somewhere. So if it is that, you have to check that whether space and S has appeared before. If not, then only you can have space and S. But if it has appeared before, then you can check for only space SP. So like that. Just follow the last day's example. How to make the entry. We will eliminate the last symbol. So I can't repeat it for today. So just go through the examples. For people who are not there on last day's class, we had finished this dictionary coding. Okay, we started with LZ78, and LZ78 has an issue of I, C, where the index and the code words both has to be taken care of while making the encoder output. But LZW is a much more better option, because here only the index is what we are going to update. Although we will update the entry and the index, but we will only send the index for our encoding purpose. So that is why it is saving a lot of bits as well. So like that you can go on doing it. Any doubt with the process of LZW for people who already were there in last class? Anyone who were not there in last day's class? For you, it might seem a little strange for all this process, but I can only suggest you to just go and look into the videos which I uploaded already. I'll be giving the links in the course page as well, or you can just go through it. because the process and the detailed overview of LZW I have mentioned there. So just because I don't have time to go through the process once again today. Those who are there, any doubt? Should I be completing this table or is it fine so that I can move to the new one, new topic? Is it fine? At least, can anyone tell me what is coming as the 19th entry? We'll take that as sample if you are correct. AD, okay, good. Is there anyone with 15th entry? 15th? SP, correct. So you are going in a correct direction. That's what I wanted to see. So like that you go on. I don't know whether you have finished it. How many entries are you having? Have you finished? Can anyone tell me what is 22nd entry? Fine. So leave it. You don't have to perform because the tabulation and the detailed tabulation is there. I'll upload it. So it's not. Just keep this numericals with you. If time permits, later on you can practice as well. Okay. So the process is same, and the decoding also. If suppose it's given, the decoding process will also be the same, just like we did in last instance. So that's all. Today, what we are going to do is we are going to introduce with two methods. Okay. The first of its kind, because these two methods are not directly too useful, because we are using more better option compared to these two methods, but they are also very primitive, but yet very easy ways of source coding. In which the first thing that comes in is called as the run length code or RLE. For people who are doing image processing based projects or like that, I guess RLE or run length code will come into your path somewhere down the line, because you are doing DCT algorithms in which a portion is actually the RLE or the run length coding. If time permits, I would have done the DCT as well, but I don't know whether I'll get time to finish it off. So whatever it is, so we'll finish off with the run length coding at least. So the run length coding is a very simple technique actually. So we'll see that. Any doubt? Any? So we'll start with run length coding. So this is the last two topics that we are going to do with respect to source coding. Okay. So this is the name of it, RLE. We usually call this. As I told you that in DCT, which is a basic compression technique which is used in image compression, RLE being one of the blocks there. So what it does is, first of all, the properties of RLE is that it's a very simple compression technique. So that is the beauty of it, that it is a very simple technique. You will just observe that how simple it is. Next is, it is used to reduce the size of, this is what is important, repeating strings of characters. So wherever there are multiple repetition of the same symbol or same character, they can be expressed in terms of a run length coding, and that saves a lot of bit. We'll take an example, we'll show that as well. So that is the ideal observation, or that's the basic property of a run length coding. So just for example, how we are doing it. It is actually one of the techniques that's usual, as I told you, in image compression in DCT. Another part where it is used is a fax machine. Actually, in fax machine is a direct application of a run length coding. That's why the application comes in. So just take an example like this. So for example, we have a long sequence of P. Okay. Suppose we have whatever the alphabet. So suppose P is one of the sequence. So we will call this as some kind of a long sequence of P. Please check that all this sequence, whatever we are looking at, the symbols of the characters will repeat. There won't be any gap. So all are P's. For example, you replace P with number of ones, number of zeros. So suppose there are 14 odd ones and 14 odd zeros consecutively. In those cases, run length encoding is a very, very profiting solution. Okay. And in fact, that is also a disadvantage in a way. I will say that how it differs. So suppose this is a long sequence of P. So the encoding process will be nothing but P and Q, where P indicates the symbol. We usually write it this way, the symbol or the data value. So it can be either a character or in terms of zeros and 1, it can be zeros or ones. And Q is the count of the value. Okay. So this is one of the observations that we can observe. So suppose there are, instead of, suppose this is a sequence that we have 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 maybe. So what we will do is, we will do this way. 1 has appeared 9 times and 0 has appeared 11 times. So like that it will be mentioned. So this is 1, 9 and 0, 11. This is kind of a representation that run length encoding does. So basically you are representing the same thing. And when do you expect like this? Suppose you are looking at, for any data set, when you are looking at, and there's thousands of data which is coming in, and ideally the sequence will be of this nature, where a portion of it will carry some information, a portion might carry only the data bus, which is like a cyclic code or some error bit or some pilot carrier, something like that. So this sequence is pretty common in our wireless technique also. Okay, so this sequence can be represented in this way. As you can see, the first half is the element that we are referring to, and the next half is the number of times it repeats. Okay. So that's how the process is. So we'll take another example, maybe with respect to characters. Please note down this so that it's easier for you to understand. Suppose you write 9B. Okay, so B, 4, 5, 6, 7, 8, 9. Then you have 5A, 1, 2, 3, 4, 5. Then you have N. Then you have G, then you have M. So you have this many characters placed in these positions. So if I consider the number of times the repetitions are, so this has been repeating for 9 times. This has repeated for 5 times. This is only for once. This is for 2 times, and this is for 3 times. So these are the different set of repetitions that has happened. So if I just RLC if I apply, or run length coding if I apply, okay, encoding if I apply, so we will write this in terms of B09, A05, N01, G02 and M03. So this is the overall structure. Now how do we save the total number of bits in this case? Why we are actually using it? You count the total number of times the total number of bits that is required here. 9 plus 5, 14. 14 plus 6 is 20. So 20 bit is what is required when you are adding up the number of elements, each and every bit or characters if you consider. Now if you consider this much, okay, now for each of the cases what we are going to do is, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bits are required. Understood what I written over there? So after RLC what we have done is, being this representation, and if you represent each and every bit out of RLC as 1 bit, so you are actually looking at 15 odd bits. So the 20 bit which was there in the initial process, for whatever be the reason or the source, so you are making this to come as 15 bits. So intuitively we can say that there is a compression of 5 bits. Yes. So basically you are looking at a scenario like this where you are representing it. This is only a representation. You can actually represent it with respect to only 9 or 5. You can check here, I have written 0905 like that. You can omit that as well. Even if you can do that, then basically you are saving a few more number of bits in that case. Now what he is asking is that how come we are writing 9 as 3? The way we are looking at the position of this encoding is that each and every block, suppose I am writing this way. So if I write this way, does that make sense? So as if you are making a block of elements which are carrying this information. So here 9 doesn't indicate it's a decimal value which needs to be converted to binary and all. It's just that it's representing a unit. Understood? So that unit is given by 1 bit representation. That's all. Now that 1 bit can be 9, that can be 5, that can be 4 or anything of that. So the representation of RLE is or RLC is something like this. So this is what the 15 bit is all about. Also with terms of ones and zeros, we can do the same way. We can find a long sequence of ones and zeros like I showed you. The first example itself. So you can check in the first case how many ones are there? 9. So 9 and then you have 11. So 11 and 9 is 20 bits once again. Now if you add this as per the RLC rule, so basically in this case you are looking at 1 plus 1 plus 1 plus 1. So basically 4 bit representation of the whole thing. So 20 bit is compressed to 4 bit. Understood? Why it is 1 1? So this is 1 bit, this is 1 bit, this is 1 bit, this is 1 bit. That's it. So RLC works in this manner. So it's regardless of the type, it will compress. Okay, so that is the way. That's why it's simple. But there is a issue also with RLC, which is the more important factor why it is not used in many of the cases. And that is purely because suppose I have a sequence. Just check this thing out. You can check the compression ratio. Compression ratio being one of the very important parameter in image compression. In fact, you have seen that. So compression ratio will be nothing but 15 by 20 or something like that. You can find out with respect to this. For binary images, it will be like 4 by 20. So like that, you can find out what is the compression ratio. But now suppose the drawback. Looking at the drawback, suppose you have a sequence X, Y, Z. Okay. Now when you are converting this to RLC. Okay, when you are converting that using RLC, because it's a simple method of implementation. So you can write this way: X appeared 0, 1 or 1 time, Y has appeared 1 time, and Z has appeared 1 time. Right? So basically your 3-bit representation which was here, now it has been extended to 3, 3, 3 or 9-bit. And even if you can consider, if it is 9-bit, suppose arguably we can remove this 0 and that also will represent the same way. So suppose I represent this way: X repeats 1 time, Y repeats 1 time and Z repeats 1 time. Even if this is the case, you can see this happens to be 6-bit. So which was 3-bit before the coding, it has become 6-bit after the coding. So the sequence is, the main objective is to observe that whenever we are having a very long sequence of events, then only RLC is applicable. Otherwise, it can't be. Why it is useful in image compression? You were saying that for image and all. Suppose in image, when you are making it into grayscale, now you are making ones and zeros which represents a gray area. Now that's an area which is represented by a long sequence of zeros because the intensities will be same. So all those cases, RLC might be a very good option to eliminate those long sequence of zeros into much smaller space. Understood? So that is why this happens to be one of the key elements to DCT algorithm that happens to compress the image. Okay, so while you are doing your projects in ITC, please have a look at RLC or RLE, how it is used in MATLAB, using the MATLAB mostly, and try to explain me using your own examples while you are coming to the presentation. Okay. So this is all about RLC. It's not that important. It's just that this is what you have to understand out of it. And the last of the source coding which is there, because this sequence, as I told you, this is only a part of it. This is given a much better representation when we are doing the DCT. So it is only the primitive portion of it. Okay. Similarly, like we did something called as arithmetic coding. Remember, right? We did the arithmetic coding. The same way, before arithmetic coding, there is something, a prelude to it, and that is what we call as Shannon Fano Elias coding. So we'll solve that. We will take one example and we'll try to solve it. Again, you will find why arithmetic coding came into existence. So let's take this last one of our source coding technique, and that is called as Shannon Fano Elias coding. So this is a technique which happens to be again is a prelude to arithmetic coding, but it happens to give you a process of encoding the bits very similar to what the Shannon Fano technique was all about. So let's see, since we are discussing the source coding, I thought of telling you as this also. So let's see how it works. So basically take an example, we'll go right through with an example. So given x as x1, x2, x3 and x4 with the probabilities as 0.5, 0.25, 0.125 and 0.125. So 4 symbols with 4 probabilities 0.5, 0.25, 0.125 and 0.125. The question is to find the Shannon Fano Elias coding or the code words using the technique. That's the option. So what we are going to do is, just like we did for many of the processes, we will have a tabulation. We will have a tabulation where we will tabulate the symbol in the terms of the descending order, in the manner. So x1, x2, x3 and x4. Then you have the probabilities like we did again. So 0.5, 0.25, 0.125 and 0.125. So these are the probabilities. Now comes a new trick. This is where the thing changes with respect to the other techniques. Now you have something called as f of x, and you have a next set which is called as f bar x. Now what is fx and what is f bar x? F of x is the cumulative sum or cumulative sum probability function. So what does that mean? It's a cumulative summed up probability function. So what we are going to do is, we are just going to have the addition of each and every probabilities at that particular stage. For example, at the first instance, this will be 0 plus 0.5. Hence, the value of the first f of x will be nothing but 0.5. But the second one will be 0.5 plus 0.2. That is what we call as cumulative sum, and 0.5 and 0.25, 0.75 will be written over here. So f of x is a cumulative sum. So the third one will be 0.75 plus 0.125, 0.81875. And finally, when you add up this one, this will be nothing but 1.0 actually, because this is how the overall process is. So this is our f of x. Now we have f of prime x, which is a function given by, please note down this is what is important, f of cap x plus half of px. F of bar x is given by f of cap x plus half of px. Now what is f of cap x? F of cap is previous value of f of x before cumulative sum. Okay. So it is the value if cap x is the value of the element just before the cumulative sum has happened. So if I just write this way, f of 1 x. So what will it be? So I go back to the table. So before it happened, so 0.5 is the cumulated sum of with adding up 0 plus 0.5. So before 0.5 happened, the value of the f cap was 0. Okay, so the value should be 0 plus half of probability of x1. Probability of x1 is 0.5. So half of 0.5. I'll repeat once again. We are trying to tabulate this f of x and f of prime x or f of cap x here. So f bar x rather. So the f bar x is given by the equation as tabulated here. If it is equal to f cap x plus half of px. Half of px is the element that we are referring to. In this case, if we are taking f1, so f1x is nothing but 0.5 by 2. But the first element is given by f cap x, which is nothing but the previous value of fx before the cumulative sum has happened. So what will be the f2x, f2 bar x? So your f cap x is nothing but, what will be your f cap x for f2? 0.5, because before that it was the value 0.5 plus half of 0.25, which happens to be 0.625. In this case it should be 0.25. Similarly proceeding, f3 bar x is nothing but 0.8125 and f4 bar x is 0.9375. The only trick in this case is the f cap. Please understand that this is the element we are taking just before the cumulated sum has happened. So basically you have to refer back to the previous value. That's more like it. So if I just calculate the data here, so for this we got 0.25, for this we got 0.625, for this it is 0.8125 and the last one is 0.9375. So we are done with these 4 columns. We are still yet to reach to code words or the average code word length. Okay, so we need to go there. For that, what we have to do is the next column is binary representation of f bar x. Please do me a favor, do this calculation. 0.25, 0.8125 and 0.9375. Just do the binary conversion. I guess most of you know how to do it. So basically 0.25 multiplied by 2. So it's 0.5, take the 0 out. Again 0.5 multiplied by 2. It will be 1.0, take the 1 out. Since you have reached 0, you will stop there itself. So in the same manner, so this is what we are going to do. I guess you know it, but still. So 0.25 multiplied by 2. This is, we are converting it from decimal to binary, but this is a fractional value. So this is 0.5. We'll take 0. Next element is 0.5 into 2. So it's really 1.0. So we'll take 1. But when the 0 comes in over here, it becomes 0. So we have to stop our process. So we'll write the binary representation is 0.01. That's how we have to do. Okay. So 0.01. Similarly, can you tell me for 0.625 what should be the 101, 0.101. Please be very careful with that decimal value. 0.101. It's not 101. Okay, you have to write that properly. What's 8125? 8125. Just do it quickly. 1101. Correct. So 0.1101 for 9375. 111. 01. Is it? Are you sure with this one? Is it 11101? Or is it 4 ones? 4 ones, right? That's correct. So, this I'll delete. So, your elements are this. Okay. So, now you are getting a binary representation of the form. So, this is 0. This is, yeah, correct. This is how the process is. Now, the next tabulation is also quite important, that how do we calculate the length of the code word. We will first calculate the length of the code word, then the code word. This is where it is different. So, the length of the code word is represented by this formula. So, length is given by ceiling value of log base 2 1 by p of x plus 1. So this is the formula for the length of the code word. We are not still not in a position to say what is the code word. Only the length of the code word can be calculated like this. So, for example, for the first case, ceiling value of log base 2 1 by 0.5 plus 1. So, this happens to be 1. So, 1 plus 1, 2 will be the length of the code word. Similarly, if you proceed, you will get the other code words. So, I will write the length here, which happens to be 2. What will it be? I think 3. This should be 4 and this also should be 4. The process is the same. You just substitute in that equation. You will get the ceiling value. It will be like this. Now coming to the code words. Now the algorithm says the code word will be nothing but the represented binary values with respect to this many length. Okay. So you can see already you have calculated the binary representation. So basically post the decimal values, whatever we have, that will be the code word. So your code word will be 01, 101, 1101 and 111. So this is where you end up coming to a conclusion that what is your length of the code word and what are your code words. So again it is not an optimal code, but it is actually giving us a prefix code in a way. So this is the overall process. Can anyone just do me a favor, calculate HX and the L average? Because we will test something out of it. If you have the code word, if I just write the following equation or table once again. So symbol x1, x2, x3, x4. So we'll rearrange in the terms of Hoffman almost. So this is our PR, or the probability is given 0.5, 0.25, 0.125, 0.125. The code word or the codes we have received as 01, 101, 1101, 4 ones, and the length is given by 2, 3, 4, 4. So can you tell me what is HX you are getting? 1.75. Okay, so 1.75. Here nothing is there? Yes, bits per. What is L average? Remember the formula Px into Lx. So it was given by Px multiplied by L of x. So you have to multiply 2 with 0.5. So that take the summation of it. That will give you the value. So this will be coming around 2.75 bits per symbol. Now again, as per the rule, we can verify that the L average is greater than HX, which is again one of the Shannon's rule. So that is also followed. So can you find out what is eta? Eta was given by HX by L average. 63 point something. So you can imagine that using this process of Shannon Fano Elias method, we are only obtaining a value of 63%. But here, one thing to be noted that there is only 4 symbols that we are taking into consideration. If the symbols are more and the probabilities are very less, like the difference is very less, naturally your efficiency will go high. But eventually what will happen, whatever happens, that will definitely be less than what arithmetic coding gives to us. But this happens to be the prelude to arithmetic coding actually, this method. Okay. That's why I thought of telling you this as one of the techniques which are there in Shannon Fano. Like I said, LZ78 is more famous because it is superior to LZ77 or LZ technique. Okay, so like that. So this is one of the process. I'll just give you one small numerical you can try back home using the technique. You have x1, x2, x3, x4 and x5. Suppose you have these 5 symbols and the respective probabilities as given as 0.25, 0.25, 0.2, 0.15 and 0.15. So this is a given problem to do. Just try to solve using the Shannon Fano Elias method, in which there are 5 symbols and the respective probabilities. So by this process we finish off with our source coding. So if I just sum up to what we did in source coding, we actually have started long time back with source coding, starting with those cyclic codes and all. But finally what we did after CAT is primarily Huffman coding, where we did the minimum maximum variance method, we did the non-binary technique or the ternary operation, then we did the extension property or the extended Huffman coding, then we went to arithmetic coding. You can relate this to it as well. So Shannon Fano Elias method also you can add to that. Then you have the dictionary coding. In that we did the LZ78. We did the adaptive Huffman coding. I forgot about that. We did the adaptive Huffman coding. Then in dictionary coding we did LZ78. We did the LZW method. Okay. And finally we ended up with RLC or the running length input technique. So these are the different set of different variable methods which have been evolving for source coding technique. So on Monday's class when we are coming back, so I guess on Monday's class we will start with error control coding, because even after doing all this there will be a set of error that will creep in. So there is a method to solve those errors by using some techniques or something called as linear block codes. Okay, so we'll start with the error control coding on Monday.